Hello everyone, welcome to Unit 1 Lesson 4, where we are, as promised, finally going to start talking about binary numbers. So, warm up for today. So, if you remember back to last lesson, you created your own number system using circles and squares. What can we communicate using only two symbols, and is there a limit? So, think about that for a second. So what can we communicate using only two symbols? Now, we all, if you're familiar with binary, you'll know that binary is two symbols. If you aren't familiar with binary, you'll know by the end of today's lesson that binary is two symbols. Is there a limit? Well, computers use binary. So a computer can do pretty much anything. So that really means that there is no limit. So, but we're going to talk about binary and exactly what that is during today's lesson. So, activity. Let's go ahead and go into Google Classroom. And we need to go to we're in Google Classroom for Lesson 4 binary numbers. Go ahead and download the Unit 1 Digital Information Activity Guide. And go ahead and download the Flippy-Do PowerPoint for Lesson 4. So we're going to use those as we work through today's activities. And this is the lesson guide, the activity guide. It's a Word document, so it looks like this. And if we take a look at the Flippy-Do, it's a 3-page PowerPoint presentation. Let's go ahead and download that as well. So going back to the presentation, where are we at? So, nope, wrong presentation. We want this one. Oh, no, we're in the right one. All right, so one place value is two possible patterns. So when we go back to a square and circle, one place value is two possible patterns. You can have either a circle or a square because we've just got space for one item. So we've either got a circle or a square. So one place value is two possible patterns. So two place values. So we've now got enough width to have two values in there. So we've got a circle and we've got a square. And we can fill the other side with the other items. So we've got a circle, 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 square, square, circle, square, square. So two place values is four possible patterns. So, and if we go through this list here, you can see every single one of these patterns is unique. Two circles, circle, square, square, circle, square, square. And the way they've done this is on the left-hand side, they've bunched all the circles together, and all the squares together, and then they've changed the shape on the other side. So we know that on the other side it can either be a square or a circle. So we've put both a circle and a square, and then circle and a square again. So we've repeated that same pattern. So we've repeated this pattern 2 times the same value, and then we've repeated the same set pattern here of toggling from one to the other. So we started off with one, we've toggled to the other. We started off with the same one, and we toggled to the other. So 3 place values, what would that look like? So as you can see here, we started off with our copy from the previous one, circle, 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 square, square, circle, square, square, and then we just added another row of all circles, and then copied it again and added another row of all squares. So now we have 8 possible patterns. So 3 place values gives us 8 possible patterns. We can then map our patterns to a numbered list. Now, note, in computer science, we count at 0. All counting starts at 0 in computer science. So you can see our 8 possible patterns here map to a decimal value of 0 to 7. So instead of 2 shapes, what if we had 10 shapes? So let's take a look at what that looks like. So one place value equals 10 one shape patterns. So this will look familiar to you. So this is our base 10 counting system that we use. So these are just shapes. You know, they don't have a value in themselves. Just think of a shape. This could be a circle, it could be a square, it could be a triangle, it could be a rectangle, it could be a pentagon, it could be something else. I don't know. You know, they just happen to be numbers, and we associate a value with them. But it doesn't have to be. It could be a shape if it need. You know, think of it as a shape instead of a number. So one place value is 10 one shape patterns. So two places is 100 two shape patterns. So we've got our, there we go. So we've got our two places. We're going to put 0 in front of 1. We'll put 1 and a 2 and a 3 and a 4 and 5 and 6, 7, 8, and 9. So that's a 100 two shape patterns. So what comes next? So 0, 9, 9. So if we had 3 place patterns, we know that we went all the way up to 0. The first piece, we started off with 0. Second piece, we have maxed out the value. Third piece, we've maxed out the value. So what would be the next item? And this is easy. This is an easy question. What comes after 99? 100. And the reason for that is we've exhausted our second placeholder value. We've exhausted our third placeholder value. So those are going to revert back to 0. And we're going to increase the first placeholder value by 1. So where is this heading? Binary. And so I spoke about binary in previous lesson, and the lesson before that we touched on it. Well, today we're going to be introducing you formally to binary. So binary is a number system with two shapes. Think of the circle and your square. So your circle and your square is now become a 0 and a 1. So that is our binary counting system. So making organized lists counting in binary. Now when we were building our circle square patterns previously, it didn't allow us to, for our 3 position and our 4 position, it didn't allow us to fill it up with circles or just squares, and I did mention that on the when we looked at those lessons. But now we actually have the option or the ability to fill the entire row up with the same shape. So here we've got our organized list counting in binary. So if we look at the bit over to the right, which I'm going to refer to this as the least significant bit. That's a computing term that it'll become more apparent what this means as we move on. But over on the right is the least significant bit. Over on the left is the most significant bit. So let's take a look at our least significant bit. We've got this repeating pattern of circle and square, 0 and 1, 0 and 1, 0 and 1, 0 and 1. Our bit in the center here, we've got our repeating pattern of zeros, circle, circle, square, square, circle, circle, square, square. It maps to zeros, 1, 0, 1. And then over on the left, our most significant bit, we've got our circle, 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 square, 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 square. So this is our organized list. Every time we add another more significant bit, we populate it with all the same value 0, and then we populate the second set with all the same value 1. So you can see that if we ignore the most significant bit here, the third bit, we've just got our first 2 bits here. That section here is exactly the same as that section here. It's just a copy. The same as this section here is the same as this section here. It's just a copy. And then we add a new row of values to the left. So we can say 0, 0, 0 is 0. Binary 1 is 1. Decimal 1 is binary 1. Decimal 2 is binary 0, 1, 0. Decimal 3 is 0, 1, 1, and so on and so forth. So with our 3 binary bits, we can count from value of 0 to 7. So, lesson 4 activity. Let's go take a look at Flippy-Do. Well, we'll take a look at Flippy-Do in a second. So this is going to be, we'll be using the Flippy-Do, which is the one of the other supporting PowerPoint presentation that you downloaded. So Flippy-Do. So each place value represents 1 bit. So remember I spoke about bits and I spoke about the least significant bit and the most significant bit. So a bit stands for a binary digit, and a bit can be a 0 or a 1. And if we go back to electronics and back to computers, you might think, you can say a bit as being on or off, a 1 or a 0, or a high or a low. High or a low is important because if you look at a computer runs off electricity. And you got 2 different states for electricity. I'll think of it as a light switch. It can either be on or off, so the electricity can either be on or the electricity can be off. The electricity can be high or it can be low. And when we say high and low, we're talking about voltage. So high voltage in the case of computer systems is only going to be something like 6 volts, 3 volts, something low like that. So the voltage is either on or it's off, which is either high voltage or low voltage, or you can think of it as a 1 or a 0. So that's basically what a binary digit, a bit, is and how it relates to computing and electronics. So your Flippy-Do has 8 bits, which together make 1 byte. So 8 bits, very important, 8 bits is 1 byte. And side note here, a little bit of interesting tidbit knowledge. 4 bits, so you think of half a byte. What do you think that might be called? So 8 bits, half a byte, it's called a nibble. You will never use a nibble though, it's more of a fun term. Computer architecture really started off with 8 bits. Back in the 80s is when the first home computers came out that had 8 bits, and went from 8 bits to 16 bits to 32 bits to 64 bits. So most of your computers that you're using today on your desktop at home, your Chromebooks, they're 64-bit. Your iPhones, 64-bit. Now there is out there in the wild, there are computers that run in higher bits than 64. You got, after 64, you've got 128-bit, and then 256-bit, 512-bit. But we're talking about mainframes that use those kind of values. But our Flippy-Do, it supports 8 bits. Together makes 1 byte. So that's important. Remember, just remember 8 bits is 1 byte. So try out your Flippy-Do. Represent these decimal numbers in binary. So 7 and 20. So we haven't looked at our Flippy-Do yet. So let's go and take a look at our Flippy-Do. So here is our Flippy-Do. If you go to the supporting Flippy-Do PowerPoint, the first slide here just shows you how to use it. So there's a little video here of dragging the various zeros and ones over onto the row at the bottom. And as we're going through this, you can see what we have at the top here. We have our binary places. Now remember, we have for binary we have 2 places. So on the far right, if we just had a one single binary place, we could have 2 values in that. We can have either a 0 or a 1. If we added another binary place here, so 2 to the power, well, 2 to the power of 0 is 1. So I'm sorry, no, 2. Yeah, 2 to the power of 0 is 1. So it's either 0 or 1. So we have a 0 value and 0 decimal value, or we have a 1 decimal value. 2 to the power of 1 has a decimal value of 2. And then if we add more, 2 to the power of 2, so we're increasing the power each time. So basically 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, and so on and so forth, until we have our 8-bit wide flippy do here. 1, 2, 3, 4, 5, 6, 7, 8. So we have an 8-bit wide flippy do. Each position has we're increased the power by 1. And you can see here each position still has 2 places. You can see what the 2 is. There's still 2 places. It can either be on or off. Then the second column here, or the second row here, you can see we have what the decimal value for that is. So 2 to the power of 0 is 2, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 8, 16, 32, 64, 128, and so on. And then what we're doing here at the bottom is we are adding either a 0 or a 1 to represent that the decimal value at that location is either going to be set to 0, so we're going to be saying 0 times 1, or we can set it to 1, so it'll be 1 times 1. So 0 times 1. Here we've got a 0 times 2. We could equally as put a 1 times 2 here. We got 1 times 4. We're 0 times 8. 0 times 16. 1 times 32. 0 times 64. 0 times 128. So when we calculate this up, we're doing basically simple arithmetic here. So we're doing a 32 plus a 4 is 36. So once it rebuilds again, we have basically the binary representation of the value 36. So we got a 1 times 4, which is 4. We've got our 1 times 32, which is 32. We'll add them both together and we get a 36. So this is our binary representation of decimal 36. 32 plus 4 equals 36. So let's take a look at our flippy do here. So what did it want us to do? Going back to here. So try out your flippy do. Represent these decimal numbers in binary. So 7. So let's go and take a look at what 7 might look like. So it's sometimes easier to start from the left. I guess it doesn't really matter where you start from. Well, we know 128 is larger than 7, so we don't want it. Why is it not letting me select that? Okay, I guess we'll use this one here. Use the third slide because the second slide is not allowing you to drag anything. So let's go to the third slide then. All right, so we know in order to get the decimal value of 7, we know that 128 is much larger than 7. So we're going to put, we don't want any 128s. We don't want any 64s because, again, it's much larger than 7. We don't want any 32s because, again, it's much larger than 7. We don't want any 16s because, you guessed it, it's much larger than 7. We don't want any 8s because it's much larger than 7. Alright, so what do we want? We want a 4. So we want 1 times 4. So what else do we need to get an 8? Sorry, 7. So we got a 1 times 4 is 4. We're going to need a 1 times 2, which is 2. And we're going to need a 1 times 1, which is 1. So 4 plus 2 plus 1. Let me type that. 4 plus 2 plus 1 equals 7. Now, an easier way to have done that is we know that 7 is 1 less than 8 because 8 minus 1 is 7. We know that if we had a 1 in this column here, it would have been 8. And we know that 7 is less than 1. So because of that, we would know that every single column to the right would have needed to be in 1. So if we go one step further with that, and let's move our zeros off here again. So if we would represent 127 in binary. So 128, so that the most significant bit value is 128. We don't want 128 because it's 1 too high. We want 127. We know that 127 is less than 128, so by default we would know that every single one of these would need to be 1. So we can test it out. Let's go and add 1 into all of these. And then we'll be doing 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And I am not going to do the math in that, but I know that that equals 127. So let's go back to here, represent these. So we did 7. We saw it was 0, 0, 0, 0, 0, 1, 1, 1. Right, next one is 20. So how do we represent 20? So let's take our letters off, numbers off again. All right, let's start with, right, we know we're not going to need a 32 because it's higher than 20. So we are going to need a 16. So let's put 1 and 16. And we know everything else to the left of that is 0, so I'm just going to ignore those for now. So what do we add to 16 to make 20? 16 plus 8 is greater than 20, so that's not what we want. 16 plus 4 is 20. We're in at 20 already, so we know that these ones are 0. 0 and 0. And then let's populate those, because when you build out a byte of data, every single value, every single place in that byte has to have a value set. You can't leave it null. Remember, it has to be a 1 or it has to be a 0. It has to be a high voltage or it has to be a low voltage. The light has to be either on or the light has to be either off. You have to have a value in there, so you can't leave it blank. So 16 plus 4 is 20. So we're 0, 0, 0, 1, 0, 1, 0, 0. Let's go see if we're right. That was over this way, wasn't it? 0, 0, 0, 1, 0, 1, 0, 0. So represent these binary numbers in decimal. 0, 0, 0, 1, 0, 0, 1, 0. So 0, 0, 0, 1, and it was 0, 0, 1, 0. So 0, let's swap these two around. 0, 0, 1, 0. Okay, so that is, we've represented it. How do we add it up? Well, we know it tells us here it's 18, but how do we do that? We added 16, 1 times 16 plus 1 times 2. So 1 times 16 plus 1 times 2 is 18. So what's the next one? 0, 0, 0, 1, 1, 1, 1, 1. We saw there that it says 31, but let's just go and test that. Make sure the PowerPoint slides are right. Make sure I didn't type something in wrong. So what was it? 0, 0. It was, yeah. Now the logic I mentioned before, you can see all of these are 1, which means it's 1 value less than the digit after it. So or the bit that is more significant than this bit. So it's 32. 1 less than 32. So it's 31, and so it's 1 times 16 plus 1 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. Now, talking about the least significant bit and most significant bit, I've mentioned that a couple of times in this lesson, and I mentioned it in yesterday's lesson. When we say most significant bit and least significant bit, that is the bit that has the most highest value, the most amount of significance on that number, or the least amount of significance on that number. For us, 128 is the most significant bit because that has a much higher value than 1, which is the least significant bit. So when I start talking about more or less significant bits, that's what that is in relation to. Okay, so we have covered those. Let's go back to our lesson. So we did that. We did that. Right, so the Flippy-Do activity guide. So I've taken you through the example in the PowerPoint. So I want you guys to go and take a look at the Flippy-Do activity guide. So let's go and find that. Flippy-Do activity guide, we downloaded that from Google Classroom. It is Word documents here. Let's go ahead and put your name and everything on there. So, and this is your directions here. So use your Flippy-Do to answer the questions, all 4-bit numbers. So fill in the binary equivalent for the decimal numbers below. We've started the first 3 for you. So you want to do all the 4-bit numbers you can do. So we're going to go and basically 3, 4, 5, 6, 7. Remember, 4-bit allows us to count up to a value of 8. No, it doesn't. I'm sorry. 4 bits allows us to count up to a value of 1, 2, 3, 4. Which is 8 plus 4 plus 2 plus 1. It's 8, 9, 10, 11, 12, 13, 15. So 0 to 15. 7, 8, 9, 10, 11, 12, 13, 14, 15. And if we take a look at this again, it's 1 less than 16. It's 1 less than the 15, than the 5th bit, the 5th value there. So go ahead and complete all the 4-bit binary values that you can put in there. What do you notice when you compare the odd numbers with the even numbers? What might explain this? So odd numbers. Yeah, I can tell you now. Well, no, I'm not going to tell you that. You can take a look at that. So there will be something that you'll notice for all odd numbers and for all even numbers. And then once you've seen it, you'll understand why. But go ahead and write down here what your explanation for that is. So binary numbers with exactly 1. Complete the chart with all 8-bit binary numbers that have exactly 1. So we've done the first 2 for you. So the next one here is going to be 0, 0, 0, 0, 1, 0, 0, 0. And when you're writing out your binary bits here, it's always good practice to break them up into groups of 4. Put a space in every group of 4 there. So continue on with those and write down the decimal there as well. What did you notice about the decimal equivalent amounts? And then conversion practice. Find the following binary decimal numbers below. So put your binary into the Flippy-Do and determine the decimal. And then determine the binary values for each of these decimal amounts. And then when you add a 0 to the right of a decimal number, it multiplies the value by 10. For example, 15 becomes 150. What similar result happens to the value of a binary number when you add a 0 to the right? So, for example, 110 becomes 1, so 11 becomes 110. Do the binary numbers 0011 and 00011 have the same value or different values? You can plug that into your Flippy-Do if you need to determine that. Would 2 bits be enough to assign a unique binary number to each vowel in the English language? And explain why or why not. how many bits would you need if you wanted to count up to the decimal number 1000? So go ahead and see if you can figure that out. And it looks like for some reason this is duplicated. It's interesting. Yeah, okay. Yeah, so you got two sets of the same values in here. So just do the first two pages. The page 3 and page 4 are duplicates of page 1 and page 2. So go ahead and work through your activity guide. Pause the video for now and then come back once you've completed that. Okay, so hopefully you enjoyed playing with binary there, and this is proving interesting for you. Today's wrap-up. So decimal number. We know a decimal number is a base 10 number with 10 possible different digits, 0 through 9. A binary number is a base 2 number with 2 possible digits, 0 through 1. So same number represented 2 different ways. So on the left here, we have our decimal. So if you look at the units, and I'm sure if you go back to elementary school, you did tens and units, hundreds, tens and units, thousands, hundreds, tens and units. So our units is 1, our tens is 2. We know that that's 2 times 10 and 2 times 1, that's 23. So going over to our decimal, we've got our 0 position, which is 1. We've got our 1 position, which is 2. With the 2s, the 4s, the 8s, and the 16s. So the binary for that is 10111. So now we've had a chance to practice. Let's find out what we've learned and what we still have questions about. Write down in your journal, so 3 things that you have learned today, 2 things you found interesting, and 1 question you still have. And then, so just a reminder today, a bit is a contraction of binary digits. Computer science love to have acronyms and contractions, so you will get used to seeing that. Get used to it because you're going to see many of them. So a bit, a single unit of information on a computer, typically represents as a 0 or a 1. And remember that there are 8 bits in a byte. A byte is important. We're going to be touching on that later. So that is the end for today. Hopefully you all enjoyed that lesson and learned something new all about binary. And I will speak to you again for our next lesson.